Hello and welcome back. So in this video, we'll look at how to use Newton-Raphson's method to still solve this same equation, right? So basically, to use Newton-Raphson's method, right? Newton-Raphson's method is just an improvement on the bisection method. Why? Because bisection, unlike bisection where you would have to bisect or divide a certain interval several times until you zoom into the root or get a value closer to the root. Newton-Raphson's method makes use of the derivative. Bear in mind, we said that the function f of x should be continuous, right? So once the function is continuous, it means that we could actually find the derivative, f prime of x. So it means that we should, if you can get the function and its derivative, then all you have to do is just get an initial guess. So unlike bisection that makes use of a given interval AB, Newton-Raphson's method makes use of an initial guess x naught, right? So depending on your initial guess, right, the Newton's method would zoom in or approach the root faster. If you get a very wrong guess, then you may never converge to the answer. But then if you can get a correct initial guess, then you can easily get to the answer very fast. And Newton's method is way faster than the bisection method once your guess is correct. So once you get a proper guess, right, then all you have to do, your new xn would be given as what? So let's say your first in x1, that's the approximated root, would be x naught minus the functional value divided by what is derivative, the functional value of the derivative of the initial guess. So this should be x naught and then this should be x naught, right? So basically this is how you do it, and then you keep repeating this until f of x1. So you check whether f of x1 is equal to 0 or the absolute value of f of x1 is what? Less than 0, less than the tolerance. So if this either of this is true, then you stop and then you return that your root should be equal to what? X1, right? But if this is not true, then you have to now find a certain x2 which will be equal to x1 minus f of x1 all over f prime of what? X1. You continue this until this condition is true. So to get a general form of this, that will be xn plus 1 to be equal to xn minus f of xn all over f prime of what? Xn. So basically this is what we do, right? This is how we make use of the Newton-Raphson's method. So let's quickly look at how to write the code for the Newton-Raphson's method. So I'm still going to use the terminal, and let me quickly close this side, and then let me exit this code, and then now I know what Newton.py, right? So .py. Okay, so here when you hit enter and then we start, so you can put your comment Newton-Raphson's method or something. Newton's method. So basically we still define our function. Def f of x should what? Return what? Bear in mind that depending on the function you are given, right, you can choose to import maybe math to make use of it. So imagine our function is not a quadratic function, but then maybe ex squared times sine x over 2 and all those things. Then you would have to import math module to do that. But since this is just a basic, so our equation was 3 star what? X squared, right? And then plus, I think 2x, so 2 star x. I said you can put this into parentheses if you want it, if you want to understand or maybe look at it properly. So this is our function. Then we also make use of the derivative, right? So def df of x. So one interesting thing to do is to solve the derivative by hand and then return the function you've got, right? But if you want Python to do it for you, then you have to install the SymPy, so symbolic Python, that would do derivative for you, but that would also take time, and then you have to write a lot of code. So I would advise you do the derivative by hand on paper, and then you just write the function. So if you differentiate this, we get 6 star what x plus 2. So basically this is the derivative of this function. So now that we have a function and its derivative, then we can now have our what? Newton-Raphson, right? So Newton's code or something. So okay, so now I define a function called maybe Newton. You can call it anything at all you want, but then this function we said would get an initial guess x naught, or maybe it could be x, whatever you want, and then a certain tolerance that would determine where the function should converge or stop, right? Then here, while we are inside a function, we first check, right? Here, when you check this, you realize that since we are going to divide f of x by the derivative, we don't want the derivative, the functional value of the derivative at x naught or any xn to be what? 0. It must never be 0, because once it's 0, this whole thing becomes undefined, and then we get a problem, right? So we don't expect it to be what? 0. So it means that we would have to check that condition. So if d of f at x is equal to 0, then we do what? We return that. So your initial guess, improper. So let me just say improper initial guess. Let me call it initial guess. Then you put the x inside that, right? But then else if, then we check that this should be elif. Else elif, the functional value at the initial guess is equal to 0, then we already have our root, right? So we just return what? Always make sure you check your indentation, so because they are very important. We return the roots, so we can say first before we return the roots, we assign the root to be equal to what? Certain x, right? The guesswork, because then it means we really guessed right. So you return the roots. Okay, but then if all this doesn't work, so you can just bring another else here, right? Then this time around we focus more on, okay, we bring this on here, else then we start with our migration. So we check, right? But here we do while our x naught, so f of x naught, f of x, here we didn't use x naught, so you keep f of x is not equal to 0, or the absolute value, right, abs of functional value of x at the guess side is what? Greater than 0, than the tolerance given. Okay, then we do what? While this is, so whilst, sorry, I have to bring another closing parenthesis here so that they are equal. Okay, so while this is not true, right, it means that while the functional value is not 0, or the absolute value is greater than the tolerance, then we should what? Do the assign x to be equal to x minus the functional value, that's f of x, divided by d of x, df of x, something like this. So basically what this is going to do is that it will take the initial x that you provided, right, this initial x, and subtract the functional value divided by its derivative from it, and then reassign it to x, and then it comes back here and checks whether the functional value of this x is not equal to 0 or this. Then it keeps iterating, it keeps doing this until one of these is met. Either it's equal to 0 or is less than the tolerance. So if this is true, then we say that it should what? Say our root is equal to x, and then it should return the root for us. Return the root, as simple as this. So basically this is it. It shouldn't be more than this. It's quite really short. I could have even returned x straightforward, but I wanted this to be readable and then maybe more understandable. So now we can call our function. So we can say answer to be equal to Newton of what? So here we can guess. We knew that. Bear in mind that if you're not giving any initial guess, you'd have to use calculator to solve the function first and then get a certain value, right? And then you use it. We realized that one of the answer was around 0.33. So we can say our initial guess is 0. Then we can give it a tolerance of 0.000001. Okay, so you can either do this or you can even set an initial tolerance here, just in case the person running the code forgets to put a tolerance there, right? So that your code will always run regardless, right? Then we print what? The answer, right? So basically we are done. So I can Control O to save and then open the terminal and then see what happens here. So I can do this and then say that, okay, Python 3, and then the name of the file is newton.py. Once I run this, we get a 0.003333 like that. So that's 1. And then what if I change the guess value to maybe negative 0.5? 0.5 here. Control O to save. Then I can as well get what? The negative 1, right? What if I change this to 0? What happens? And I do Control O to save. Then if I run it, I still get a 0.0003. What if I make it negative 0? This is just something silly I want to try. Negative. Oh wow, we already even made this negative 0. Okay, so negative 0.1. Let's see which of the roots it will zoom to, right? Control O to save. And then it still came to the 0.3333. So you see, basically this is how we use Newton-Raphson to solve this same function. Bear in mind that you write the function, make sure you return the functional value you are given. If there is exponent, logs, and ln and sine and cosine inside your function, then you have to first import math to do that for you, right? And then you can now write the functions here. Then after writing the function, you'd have to differentiate the function on paper and then write the derivative, the answer you've gotten for your derivative here. Make sure you check for zeros of the derivative. So if the derivative will give you 0, then you would say no, we don't want that. So let's see which value of x will make this derivative 0. If x is, let me see, 1/3, this becomes 2, so negative 1/3, right? So let's use negative 1/3 here and see what happens. So if I change this to negative 1/3, 1/3, let's see what happens. Sorry. And I Control O to save, and I do this. It tells me that improper initial guess, this, right? So it means that this value will make the derivative 0, and we don't want that. So it just does that improper initial guess value like that. So basically this is how you write for Newton-Raphson. I'll end the video here, and then in the next one we'll look at the second method. Thank you.